Welcome to the Introduction to Electrochemistry. Electrochemistry involves the study of any and all reactions in which a transfer of electrons takes place. So in this chapter, very similar to thermochemistry when we looked at an exchange of heat, in electrochemistry we're going to look at an exchange of electrons. Some reactions in our everyday life produce electricity, such as the batteries that we use for our electronic devices. Some reactions actually require electricity, such as the electrolysis of water or recharging your batteries, and some reactions will occur where no electricity is produced or used at all. When we look at electrochemistry and we look at reactions that involve the transfer of electrons, we're actually looking at oxidation and reduction reactions. Oxidation and reduction reactions are reactions in which electrons are transferred from one substance to another. In oxidation, we look at reactions where electrons are lost, and in reduction, we look at reactions where electrons are gained. This can be compared to endothermic and exothermic reactions that we looked at in the thermochemistry chapter. Exothermic reactions when heat was lost. Oxidation is when electrons are lost. Endothermic reactions was when heat was gained. Reduction reactions is when electrons are gained. It's the same thing. When we write out the reactions, the electrons will be written either as a reactant or a product, just like heat was written as a reactant or a product. So again, oxidation and reduction reactions are reactions in which electrons are transferred from one substance to another. Instead of saying oxidation and reduction reactions, as it's quite long, we can reduce this down to redox reactions. Think of it as we're Brangelina-ing it. Reactions in cellular respiration, combustion reactions, and chemical reactions that occur in batteries to give us power are just a few of the types of reactions that constitute redox reactions. Let's look at an example. A zinc strip is placed in a solution of copper 2 sulfate. In order for us to examine this from an electron sense, we need to first write out the non-ionic equation, then the total ionic equation, and finally the net ionic equation. This is something that was discussed in the Solutions chapter of Chemistry 2202, and it's at this point you may need to review those notes as we'll be moving quickly through this topic. The non-ionic equation is just basically the balanced chemical equation, where you might need to go back to Science 1206 as well. We have a zinc strip, so we would represent that as zinc solid, and it's placed in a solution of copper 2 sulfate. If you think of copper 2 sulfate, the copper 2 is telling you that this is Cu2 positive, and sulfate is on the back of your periodic table, remembering that this is a 3202 topic, so you will have that for your exam. Sulfate is SO4 2-. If you were to write the crisscross in order to write out this reaction, notice that they have equal charges. It would be CuSO4. Then you would need to write the products for this. And again, remember from Science 1206 that the positive of one will react with the negative of the other. Zinc has a 2 positive charge, copper has a 2 positive charge, and sulfate has a 2 negative charge. Therefore, the zinc, being the positive of one, will react with the negative SO4 of the other. They will combine to make ZnSO4, and the copper will come out as lonely. Next, you would write the total ionic equation. And to write the total ionic equation, you need to break apart those substances which are actually existing as ions in that solution. And the substances that will be existing as ions in solution are those ionic compounds or acids. So the zinc solid will stay as is. That will not break up into an ion because it's in solid form. Then we have copper sulfate, CuSO4 aqueous. This is an ionic compound in aqueous solution, so this will break apart into its 2 ions, Cu2 positive and SO4 2 negative. We're almost doing the opposite of what we had to do in order to write the non-ionic equation. Copper solid will stay as copper solid, And zinc sulfate, ZnSO4 aqueous, is an ionic compound in aqueous solution, so this will also break apart into Zn2 positive and SO4 2 negative. That's your total ionic equation. Lastly, to write the net ionic equation, you need to cross out anything that's on the reactant side and the product side, and it is identical. It's like you took the compound or the element on the reactant side, you photocopied it, and you pasted it on the product side. Everything needs to be the same. The charge, if it's there, the state of matter, the number, everything. Therefore, the only thing that we can cross out in the total ionic equation is SO4 2 negative aqueous and SO4 2 negative aqueous. That is identical. Copper cannot be crossed out because we have Cu2 positive and aqueous on the reactant side and Cu0 solid on the product side. That is not the same. When everything's been crossed out, you can write down what you haven't crossed out as the net ionic equation. Zn solid plus Cu2 positive aqueous goes to Cu solid and Zn2 positive. And what you've crossed out, SO4 2 negative, remember, is called a spectator ion. From the net ionic equation, which I'll write here, so we'll remember, Zn solid plus Cu2 positive aqueous goes to Cu solid plus Zn2 positive. We can now write out what's called half reactions. And a half reaction is any reaction that involves the gain or loss of electrons with the electrons written in the equation. So just like in thermochemistry, we had a thermochemical equation where heat was written as part of the balanced chemical equation. In this unit, we have what's called half reactions, where the electrons are written in the equation. As the name suggests, half reactions, we're going to have two reactions. Half of the reaction and the other half of the reaction. And in order for us to write out the half reactions, we split apart our net ionic equation according to the element. So we're going to take Zn solid, so you see that right here, and we're going to pair that up with Zn2 positive, the same element. That goes to Zn2 positive. Then we're going to take Cu2 positive, and we're going to pair that up with Cu solid. Okay, we break it apart according to the same element. Then we need to add the number and the right placement of the electrons. And what you need to think of is you need to put the electrons and the right number of electrons, so the overall charge on the reactant side and the overall charge on the product side are the same. Also remember, and this is hard sometimes because you have to think backwards really, that electrons are negatively charged. So when you add them in, you're actually subtracting from the overall charge. For instance, let's look at the first half reaction with zinc. Zn solid on the reactant side has an overall charge of 0 since there's nothing there. Then on the product side, it has an overall charge of 2 positive. When we add electrons, since electrons are negatively charged, we will always add electrons to the higher number or the higher charge. Therefore, we need to add electrons to the same side as the 2 positive. And we need to make the 2 positive go back down to 0 to match with the reactant side. So I need to add 2 electrons because 2 positive and 2 negative make 0, which is exactly what's on the reactant side. Likewise, if we look down at the copper half reaction, I have a 2 positive charge on the reactant side and an overall charge of 0 on the product side. Again, we add electrons to the higher number, which would be 2 positive, and 2 positive and 2 negative make 0. Those are our 2 half reactions. Then, to write our overall equation, we have to cancel out anything that appears on opposite sides of the arrow, just like we were doing with mechanisms in equilibrium. And you'll notice that these 2 electrons will cancel out with those 2 electrons to write an overall reaction, meaning we'll get back our net ionic equation. Also recall from the beginning that whenever we have a loss of electrons, or electrons are on the product side, this is called oxidation. So this is the oxidation half reaction. When electrons are gained or on the reactant side, it's called a reduction half reaction. As well, whenever we have an oxidation half reaction, the reactant, here Zn solid, is called the reducing agent. And this is going to come up again on the next page, but I want to bring it to your attention now because it will make more sense in the example. When we have the reduction half reaction, the reactant, in this case Cu2 positive, is called the oxidizing agent. And the reason why they're the opposite is because of this word agent. Okay? An agent, just like an FBI agent, forces you to do something. So Cu2 positive, which is undergoing reduction, is therefore causing oxidation to occur in the other half reaction. So since copper is undergoing reduction, the other half reaction has to undergo oxidation. So it's the oxidizing agent. Likewise, since zinc or Zn solid is undergoing oxidation, it's forcing the other half reaction to undergo reduction. Therefore, it's the reducing agent. So to summarize, oxidation is when you lose one or more electrons. It is the substance being oxidized, so it is the reducing agent. Reduction is the gain in one or more electrons, so it is the oxidizing agent. These definitions are very important and will spill over to the remainder of the unit. A good memory tip that I like to tell students is to remember oil rig. If you remember oil rig, you'll remember the definitions of oxidation and reduction. Oxidation is loss, oil. Reduction is gain, rig. So if you take oil rig and put it at the very top of any assessment, you'll remember what is oxidation and what is reduction. And think of loss and gain the same way we thought of loss and gain with heat in the thermochemistry chapter. Let's go through an example. Write the two half reactions for the following. A strip of copper is placed in a solution of silver nitrate. Before we can write out the half reactions, we need to have the net ionic equation. Before we can have that, we need to write the total ionic equation and first the non-ionic equation. So, for the non-ionic equation, which is simply the balanced chemical equation. For this, you may want to have a periodic table handy. We have a strip of copper. We'll represent that as Cu solid, is placed in a solution of silver, which is Ag positive, and nitrate on the back of the periodic table is NO3 minus. If we were to write out the crisscross for this, or the formula, it would be AgNO3. You also need to look at your solubility chart to see if when NO3 negative reacts with silver, if it's aqueous or solid, and all nitrates will always be aqueous. And this will react to produce. And now we need to figure out what the products would be. And we need to do the crisscross. Remember that the positive of one will react with the negative of the other. Copper is generally 2 positive. Silver is positive and nitrate is negative. Therefore, copper 2 positive will react with NO3 negative. When we do the crisscross for that, we're going to get Cu, NO3, 2, aqueous. And that means silver is going to come off by itself. And that to give us Ag solid. If you're having trouble with this, you really need to go back to your Science 1206 notes and relearn how to write out balanced chemical equations. This is going to be very important for next year as well. So the last thing we need to do is make sure that it's balanced. You'll notice on the reactant side we only have 1 NO3, and on the product side here we have 2. So I need to put a 2 in front here to balance out the nitrates, which means I've now put a 2 in front of the silver. So I need to put a 2 in front of the silver on the product side as well. So I'll plus 2 silver. We now have a balanced non-ionic equation, which means we'll move on to the total ionic equation. Which means we need to break apart anything that is an ionic compound. Copper stays the same since it's solid. The silver nitrate will have to break apart to give us 2 Ag positive aqueous and 2 NO3 negative. So notice that the coefficient is multiplied throughout to give us Cu2 positive aqueous, since copper nitrate is ionic, and 2 NO3 negative. So notice that any of the subscripts that we put there to balance it, so we put the 2 there to balance it, comes out in front. The 3 on the NO3 stays because that's part of the original formula, plus 2Ag solid. Once you've written out the total ionic equation, you can write out the net ionic equation by crossing out anything in the total ionic equation that is identical from reactants to products. And you'll notice that's 2 NO3 negative aqueous and 2 NO3 negative aqueous. Those are our spectator ions. To give us a net ionic equation of Cu solid plus 2Ag positive, reacting to produce Cu2 positive and 2Ag solid. From there, we can now write out our 2 half reactions. And we split it up according to the elements. So I have Cu solid goes to Cu2 positive, aqueous, and I need to write out the number of electrons and put them on the right side. Copper solid has an overall charge of 0, whereas copper 2 positive has a charge of 2 positive. You always add electrons to the higher number, so I know I'm going to put them on the product side. And in order to make 2 positive become 0, I need to subtract 2 from there. Additionally, since I have put electrons on the product side and I am losing these electrons, remember oil rig, oxidation is loss, so this is my oxidation half reaction. Since this is my oxidation half reaction, Cu solid is also my reducing agent. The other half reaction would be 2Ag positive, aqueous, goes to 2Ag solid. Here I have an overall charge on the reactant side of 2 positive, 2 times the positive, so that's 2 positive in total, and 0 on the product side. We'll always add electrons to the higher number, so here I have to put them on the reactant side. And in order to make 2 positive 0, I need to add 2 electrons. The other thing you will notice about oxidation and reduction reactions is the fact that we always have to have one oxidation reaction and one reduction reaction, which means you'll always add electrons on opposite sides from one half reaction to the other. If you notice you put them on the same side, it means you've done something incorrectly. Since the second half reaction we're gaining electrons, this is reduction, and therefore the Ag positive is the oxidizing agent. Let's try this final example. Sodium chloride can be produced from sodium metal and chlorine gas. Let's write out the half reactions. Well, in order to write out the half reactions, we first need to write out the non-ionic equation, or the balanced chemical equation. So we have sodium chloride can be produced from, so we start off with sodium metal, so Na solid, and chlorine gas. And again, remember from Science 1206, when chlorine is by itself, it's actually Cl2, it's diatomic. And this is going to produce NaCl. I'm going to put that down as aqueous solution. You can also put it, since it's a solid and a gas, we can also think of it as the crystalline solid as well, up to you. In order to balance this, I have 2 chlorines here, so I need to put a 2 out in front here, and therefore I put a 2 in front of the sodium, so we need to put a 2 in front here. Then we write out the total ionic equation, so we break apart any ionic compounds. So 2Na solid stays the same because it's in solid form. Cl2 gas stays the same, that's not in ion form. And we have 2Na positive aqueous and 2Cl negative aqueous if we had kept that as aqueous. You should notice that nothing can cancel out here, so our total ionic equation is also our net ionic equation. Therefore, we can break this apart into its two half reactions. 2Na solid goes to 2Na positive, aqueous. And Cl2 gas, we'll put in the electrons after, goes to 2Cl negative. Going back to the first half reaction, on the reactant side, this has an overall charge of 0. On the product side, we have an overall charge of 2 positive. We can only add electrons to the higher number, so I'm going to have to put those on the product side. And again, in order to make 2 positive go down to 0, we have to subtract 2. For the second half reaction on the product side, or on the reactant side, we have an overall charge of 0. On the product side, we have an overall charge of 2 negative. We can only add electrons to the higher number, and 0 is higher than 2 negative, so we'll put them on the reactant side, which we would have predicted. Since we put them on the product side in the first half reaction, we have to put them on the reactant side in the second one. In order to make 0 go down to 2 negative, I need to add 2 electrons. If this had asked us to write out the overall reaction, we would cross out those 2 electrons. Thinking about oil rig and having to determine which one is oxidation and which one is reduction. So oil rig, oxidation is loss, reduction is gain. In the first half reaction, I am losing electrons, so this is oxidation. In the second half reaction, I'm gaining electrons, so this is reduction. Since the first half reaction is the oxidation half reaction, we also have the reducing agent. Since the second half reaction is undergoing reduction, we also have the oxidizing agent. Remember that those are always the reactants, so 2Na here is the reducing agent, and Cl2 gas here is the oxidizing agent. Change that to an A. And there you have it. At this point, you can now go to the worksheet and you can work on questions 1 and 2.